This evening, we're going to delve into something that appears straightforward, but actually represents one of the most astonishing ideas in the entirety of scientific thought: a light year. You've likely encountered this expression countless times. Researchers employ it regularly when discussing outer space. However, here's what the majority of individuals fail to recognize. When you genuinely comprehend what a light year signifies, when you completely grasp the span it indicates, it transforms your perception of the cosmos. It isn't merely a large figure, it's a span so immense that it tests our capacity to fathom it. And when this exploration concludes, you're going to comprehend precisely why astronomers require this unit, and why no alternative would be effective. Before we proceed any further, if you appreciate this type of thorough investigation, a quick like or subscribe genuinely supports the channel's development. It's a minor action for you, but it creates a tremendous impact for me. Now, let's begin. Let's start with something recognizable: span. You comprehend span in your daily existence. You're aware of how distant the supermarket is, your place of employment, the neighboring town. These are spans you can connect with because you've journeyed them. You possess an understanding of what they represent in relation to duration, in relation to exertion, in relation to what you'll observe during the trip. A kilometer represents roughly the span you can walk in 10 to 12 minutes at an ordinary pace. These units function perfectly adequately for daily existence. If somebody informs you the shop is 5 kilometers distant, you're aware approximately how much time it'll require to drive there. You can envision the trip in your thoughts. Perhaps you'll encounter several signal lights. Perhaps you'll observe some recognizable points of reference. The span is tangible and relatable. If somebody mentions a town is 200 kilometers distant, you can arrange your journey appropriately. That's roughly 2 hours of travel. You'll need to replenish your fuel reservoir, perhaps take along some refreshments. Organize for a break midway. These spans are scaled to human experience. They correspond to our existence and our understanding. We've developed to comprehend spans we can traverse in a day, spans we can observe, spans that are significant for continuation and wayfinding. However, these units begin to become unwieldy when we discuss genuinely enormous spans. The span from New York to Los Angeles is roughly 4,500 kilometers. That's still controllable as a figure. It's roughly a 5-hour journey by aircraft. Individuals complete that voyage regularly. They traverse the mainland. They observe the terrain transform from eastern seaboard urban areas to central flatlands, to mountainous peaks, to southwestern arid regions, and ultimately to the Pacific shoreline. The voyage is extended, but it's attainable. It's within human possibility. You can picture completing that expedition. The Earth's perimeter at the equatorial line is roughly 40,075 kilometers. That's a substantial figure, but it's still something we can process intellectually. Historical voyagers sailed around the globe, so we're aware it's achievable to journey that span, even if it requires many months. Ferdinand Magellan's expedition required 3 years to navigate the globe from 1519 to 1522. Contemporary passenger flights can orbit the Earth in roughly 45 hours if you could arrange connecting journeys that proceeded completely around. The Earth is enormous from our viewpoint positioned on its exterior, but it's not unfathomably enormous. It's a limited thing you could theoretically investigate entirely. But now, let's expand further. The span from Earth to the Moon is roughly 384,000 kilometers. This is where standard units begin to seem insufficient. 384,000 kilometers. That's difficult to picture in any significant manner. It's not comparable to traveling across the nation. It's not comparable to navigating around the globe. It's something entirely different. There's no pathway to pursue, no points of reference to encounter, no pause locations throughout the route. It's simply span, pure span across vacant space. How would you even commence to journey that distant? The Apollo space travelers required roughly 3 days to journey from Earth to the Moon, utilizing powerful propulsion systems that propelled them to velocities of roughly 11 kilometers per second. That's roughly 39,600 kilometers per hour, approximately 400 times more rapid than motorway travel. Reflect on that momentarily. 400 times more rapid than you've ever operated a vehicle. And even at that remarkable velocity, which demanded some of the most powerful propulsion systems ever constructed, consuming massive quantities of propellant, it still required 3 days. 3 days of journeying through vacant space at velocities no human had ever encountered previously, merely to arrive at our closest heavenly companion. And that's merely to the moon, the nearest heavenly object to Earth. The moon is so proximate, you can observe it with your unaided vision. You can observe characteristics on its exterior with a set of field glasses. It's directly there, suspended in the atmosphere. And yet, it requires 3 days of propulsion journey to arrive at it. When we begin discussing the span to additional planets, to the sun, to additional stars, kilometers become entirely useless. The figures get so enormous that they forfeit all significance. They become theoretical symbols on a sheet rather than spans you can connect to in any manner. The span from Earth to the Sun is roughly 150 million kilometers. Attempt to picture that. You cannot, can you? Your mind simply perceives it as a genuinely enormous figure, but you don't possess any instinctive understanding of what it signifies. There's nothing in your everyday existence that conditions you for a span like that. Nothing in human development conditioned us to contemplate spans this enormous. We developed to comprehend the span to the subsequent water supply, the span to the foraging territories, the span we could traverse in a day. We didn't develop to grasp 150 million kilometers. The Apollo vessel that transported space travelers to the moon journeyed at roughly 11 kilometers per second on average. At that velocity, it would require roughly 160 days, over 5 months to arrive at the sun's span. The most rapid vessel humans have ever constructed, the Parker Solar Probe, journeys at velocities up to 192 kilometers per second when it's proximate to the sun, utilizing its gravitational force to propel itself to increasingly higher velocities. Even at this remarkable velocity, which is roughly 17 times more rapid than the Apollo vessel, the probe still requires many months to finish its circuits around the sun. And the star is proximate. It's directly here in our astronomical vicinity. It's the star we circle. It's the origin of all the illumination and warmth that renders existence on Earth achievable. We observe it daily. It's recognizable. And yet, it's 150 million kilometers distant. A span so immense that even our most rapid vessel requires many months to traverse it. When we begin discussing spans to additional stars, even the sun's span becomes minuscule by comparison. The sun is our closest star, and it's 150 million kilometers distant. The subsequent closest star, Proxima Centauri, is roughly 266,000 times more distant than that. 266,000 times more distant than a span that already requires our most rapid vessel many months to traverse. This is why astronomers required a distinct measurement unit. Not because they prefer creating complications, not because they desire to perplex individuals with enormous figures, but because kilometers simply don't function when you're calculating astronomical spans. Utilizing kilometers to calculate spans to stars would be comparable to utilizing millimeters to calculate the span between nations. Technically achievable, but entirely impractical. The figures become so enormous, they forfeit all significance. They cease being spans and become merely figures, theoretical mathematical ideas that don't link to anything in our understanding. So, astronomers devised something different, the light year. But here's what you need to comprehend immediately from the beginning. A light year is not a calculation of duration. I'm aware it contains the term year in it, which causes it to appear like duration, but it's not. A light year is a calculation of span. It's the span that illumination journeys in 1 year. Now, why establish a unit on illumination? Because illumination is distinctive. Illumination is the most rapid thing in the cosmos. Nothing can journey more rapidly than illumination. It's not merely a velocity restriction that we haven't surpassed yet. It's a basic principle of natural science. The velocity of illumination is a fixed value, unchanging, identical everywhere in the cosmos. Whether you're on Earth, on Mars, in another stellar system, or at the boundary of the perceivable cosmos, illumination always journeys at the identical velocity. Illumination journeys at roughly 300,000 kilometers per second. Let me state that once more, because it's significant. 300,000 kilometers per second. Every individual second, illumination journeys 300,000 kilometers. This isn't an estimate or a projection. It's been calculated with exceptional accuracy. The precise figure is 299,792.458 kilometers per second, but for our intentions, 300,000 kilometers per second is sufficiently accurate. That's remarkably rapid. To position it in viewpoint, illumination can journey around the Earth's equatorial line roughly 7.5 times in 1 second. In the duration it requires you to snap your digits, illumination could orbit the entire planet numerous times. In 1 second, illumination could journey from New York to Los Angeles and return roughly 37 times. It's a velocity that's nearly impossible to picture because nothing in our daily understanding moves anywhere close to that rapid. The most rapid thing most individuals encounter is an aircraft. A passenger jet travels at roughly 900 kilometers per hour, or roughly 0.25 kilometers per second. Illumination journeys over 1 million times more rapidly than that. The most rapid automobile ever constructed, the Thrust SSC, achieved roughly 1,200 kilometers per hour, or roughly 0.33 kilometers per second. Illumination is roughly 900,000 times more rapid. Even the most rapid vessel we've constructed, the Parker Solar Probe, at 192 kilometers per second at its maximum, is still only roughly 0.064% the velocity of illumination. It's traveling remarkably rapidly by human benchmarks, but compared to illumination, it's progressing slowly. When you activate an illumination switch, the illumination arrives at your vision essentially instantaneously, because the chamber is so limited. The illumination journeys from the source to your vision in roughly 10 billionth of a second. That's so rapid that there's no detectable postponement. As far as your mind is concerned, the illumination manifests instantaneously, but the illumination did journey. It required duration. It's simply that the duration was so brief, you couldn't conceivably detect it. When you observe the sun in the atmosphere, you're genuinely observing it as it existed 8 minutes and 20 seconds previously, because that's how much duration it requires illumination to journey from the sun to Earth. The sun is so distant that even illumination traveling at 300,000 kilometers per second requires over 8 minutes to traverse the span. This has an intriguing consequence. If something occurred on the sun immediately, if it unexpectedly transformed color, or dimmed, or even detonated, we wouldn't be aware for over 8 minutes. The occurrence would happen, but the illumination conveying data about that occurrence would still be journeying toward us. We'd continue observing the sun as it existed, not as it is, for over 8 minutes. When you observe the moon, you're observing it as it existed roughly 1.3 seconds previously. Not substantial postponement, but still postponement. When space travelers traversed on the moon and communicated to mission headquarters on Earth, every utterance they expressed required 1.3 seconds to arrive at Earth. And every reply from mission headquarters required 1.3 seconds to arrive at the moon. This generated a nearly 3-second interval in every exchange. You can detect this postponement in the documentation. There's always this interruption, this delay, because the transmission signals conveying their utterances journeyed at the velocity of illumination. And even illumination requires duration to traverse the span between Earth and the moon. Illumination doesn't journey instantaneously. It possesses a velocity, and that velocity, while remarkably rapid, is still limited. This is one of the most significant breakthroughs in natural science. Before the late 1600s, most individuals presumed illumination journeyed instantaneously. You opened your vision and you observed things immediately. So, it appeared like illumination must be instantaneous. But in 1676, a Danish observer named Ole Rømer made a meticulous observation of Jupiter's satellites and detected something peculiar. The durations when the satellites vanished behind Jupiter varied depending on where Earth was in its circuit. When Earth was nearer to Jupiter, the eclipses occurred earlier than anticipated. When Earth was more distant from Jupiter, they occurred later. Rømer comprehended this was because illumination required duration to journey the different spans. He determined that illumination required roughly 22 minutes to traverse the diameter of Earth's circuit. His determination wasn't entirely correct because he didn't possess knowledge of the precise magnitude of Earth's circuit. But he demonstrated that illumination possesses a limited velocity. Today, we possess knowledge of the velocity of illumination with exceptional accuracy. We've calculated it utilizing laser devices, atomic chronometers, and advanced apparatus. We've verified that it's fixed, that it doesn't transform depending on how rapidly you're traveling or where you are positioned. And we've uncovered that this velocity, this fixed value, is integrated into the fundamental structure of the cosmos. It's not merely the velocity that illumination happens to journey at, it's a basic characteristic of spacetime itself. So, a light year is the span illumination journeys in 1 year at this velocity. Let's determine that. Illumination journeys at 300,000 kilometers per second. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. If we multiply all of these together, 300,000 times, 60 times, 60 times, 24 times 365, we obtain approximately 9.46 trillion kilometers. To be more accurate, it's 9,460,730,472,580.8 kilometers. But for straightforwardness, we typically just state 9.46 trillion kilometers. That is what a light year represents. 9.46 trillion kilometers. It is not a measure of time, but a measure of distance. The distance that light, the fastest thing in the universe, travels in 1 year. And that is the quantity we are going to try to make sense of tonight. Because understanding what a light year truly means is essential for understanding our place in the universe, the distances that separate stars, and the real scale of the cosmos. But before that, we need to talk about what a trillion really represents, because most people have no intuitive sense of how enormous that number actually is. We casually use words like million, billion, and trillion in everyday life. We hear about government budgets measured in the trillions, about billionaires, about millions of people, but we rarely grasp the vast differences between these numbers. They all sound like large quantities, so we tend to group them together in our minds as if they were similar. Yet they are not. The gaps between them are staggering. A million is 1,000 thousands. If you saved $1 every single day, starting today, and continuing without ever stopping, you would reach $1 million in about 2,740 years. That is a very long period, but still something you can at least imagine. You can picture a historical timeline stretching back 2,740 years. That takes you back to classical Greece, to the early days of the Roman Republic, to an era when humans were already founding cities, writing texts, and building complex societies. It is a span of time the human mind can, with effort, conceptualize. A billion is 1,000 millions. Now we are increasing by a factor of 1,000. If you saved $1 every second, not every day, but every single second, you would need roughly 32 years to accumulate $1 billion. That is longer than the time it takes for an entire generation to grow up. If you began counting seconds at the moment you were born, and continued counting without ever sleeping, eating, or taking any kind of break, you would be about 32 years old when you finally reached 1 billion. Consider that difference. 1 million seconds corresponds to about 11½ days. That is manageable to imagine. You can picture a period of just under 2 weeks. But 1 billion seconds corresponds to 32 years. The leap from a million to a billion is immense. A trillion is 1,000 billions. At this point, numbers start to detach from anything in normal human experience. If you tried to count to 1 trillion, saying one number every second without pausing, it would take you roughly 31,700 years. To put that into perspective, that is longer than the entirety of recorded human history. Agriculture, which forms the foundation of civilization, began only around 10,000 years ago. Before that, humans lived exclusively as hunter-gatherers, moving across the land, following migrating animals and seasonal plants. Writing systems first appeared roughly 5,000 years ago in Mesopotamia. The pyramids in Egypt were constructed about 4,600 years ago. The wheel was probably invented around 5,500 years ago. To reach 1 trillion in a continuous count, you would have had to start long before any of these developments. You would have needed to begin counting when humans still lived in small tribal bands, when there were no cities, no states, no writing, no farming, no permanent villages. You would have been counting throughout the entire duration of human civilization. Through every invention, every scientific breakthrough, every empire that rose and fell, through every conflict and every peace, every success and catastrophe recorded in human history. And even today, you would still be counting, with thousands of years still remaining before you finally arrived at 1 trillion. To make this even more tangible, think about this. 31,700 years ago, modern humans were enduring the last ice age. People relied on stone tools. They hunted woolly mammoths and giant ground sloths. Our species had only just begun to spread widely across the planet. Modern humans had relatively recently left Africa and were in the early stages of settling Europe and Asia. There was no language in the sophisticated form we know today, no art beyond simple cave paintings, and no technology beyond sharpened stones and wooden spears. That is how far back in time 1 trillion seconds would take you. And a light year corresponds to 9.46 trillion kilometers. Each one of those kilometers is a real physical distance. It is not an abstract symbol. It is the distance you could cover on foot in roughly 10 to 12 minutes at an average walking pace. And there are 9.46 trillion of those individual kilometer segments in a single light year. 9.46 trillion separate, distinct kilometer-long stretches, each one comparable in length to the walk from your home to a nearby shop. So when we say that a light year is 9.46 trillion kilometers, we are referring to a distance that utterly dwarfs anything in everyday human experience. You can write the number down. You can plug it into formulas and use it in calculations. You can manipulate it in equations with ease. But truly feeling what it represents in your gut is almost impossible. Human brains did not evolve to work comfortably with such enormous magnitudes. We evolved to track the number of people in a group, the size of a herd, the number of days until the weather changes. We can count to a few hundred, possibly a few thousand if we push ourselves. But 9.46 trillion is so far beyond those limits that psychologically, it almost feels infinite. The most effective way to get a sense of a light year is to build up to it gradually, starting with distances that feel familiar and then increasing step by step. We are going to make that journey slowly, moving from the known to the unknown, and watching as scales that once seemed huge become tiny compared with what comes next. Let us begin with 1 light second, which is 300,000 kilometers. That is roughly the distance from Earth to the Moon and 3/4 of the way back. Think carefully about what that implies. Light leaves Earth, travels all the way to the Moon, which is 384,000 kilometers away, reflects or returns, and gets about 3/4 of the way back to Earth. And that entire round trip happens in a single second, one single heartbeat of time. During the Apollo missions, when astronauts stood on the Moon and spoke to Mission Control in Houston, there was a communication delay of about 1.3 seconds in each direction. The astronauts would say something, and the people in Houston would not hear it until 1.3 seconds later, because the radio signal, traveling at the speed of light, needed that much time to cross the distance. When Mission Control answered, their reply needed another 1.3 seconds to reach the Moon. That meant each exchange naturally included a delay of nearly 3 seconds. When you listen to the recordings, you can notice the pause, that slight lag between question and answer, caused entirely by the distance the signals had to cover, and by the fact that nothing, not even radio waves, can exceed the speed of light. 1 light minute is 60 light seconds, or 18 million kilometers. The Sun is roughly 8 light minutes from Earth, a distance of about 150 million kilometers. So 1 light minute represents around 12% of the distance between Earth and the Sun. If you could somehow stand on the surface of the Sun, which you obviously cannot, because it is a sphere of plasma with a surface temperature of about 5,500 degrees Celsius, and look toward Earth, you would be seeing Earth as it appeared 8 minutes and 20 seconds in the past. If Earth were to suddenly be destroyed, you would not see it happen right away. For more than 8 minutes, Earth would still appear intact, because the light carrying information about that catastrophe would need that long to cross the gap between the two worlds. This delay has very real consequences for space exploration, consequences that are easy to overlook. When space agencies operate robotic vehicles on Mars, there is always a built-in communication delay because of the distance involved. At its closest alignment, when Earth and Mars are on the same side of the Sun in their respective orbits, Mars is about 32 million kilometers from Earth, roughly 2 light minutes. At its farthest, when the planets are on opposite sides of the Sun, the distance can be around 400 million kilometers, or about 22 light minutes. This means that when the Perseverance rover is working on the Martian surface, each command sent from Earth takes between 2 and 22 minutes to arrive, depending on where Mars is in its orbit. Any data, images, or measurements that Perseverance sends back to Earth require the same amount of time to return. You cannot drive a rover on Mars in real time the way you would control a remote-controlled car on Earth. The signal delay is simply too large. Instead, engineers have to plan the rover's activities carefully and in advance. They study images from previous days, design a driving path, write a full sequence of commands, transmit those instructions to Mars, and then wait. If something goes wrong, if the rover becomes stuck or encounters an unexpected rock or slope, the team cannot respond immediately. They must wait for the rover's status data to arrive on Earth, which takes anywhere from 2 to 22 minutes. Then they have to analyze the problem, decide on a solution, prepare new commands, send them to Mars, and wait again for them to be received. A simple issue that could be solved in seconds with a remote-controlled vehicle on Earth can easily take an hour or longer to resolve on Mars. 1 light hour is 60 light minutes. That corresponds to about 1,080,000,000 kilometers, a bit over 1 billion kilometers. Now we are dealing with distances so large that even our fastest spacecraft crawl by comparison. The planet Saturn, at its closest approach to Earth, is roughly 1.2 light hours away. Saturn is among the most distant planets visible to the naked eye from Earth, a stunning ringed world that humans have observed since antiquity, and it sits around 1.2 light hours from us at its nearest. When the Cassini spacecraft orbited Saturn between the years 2004 and 2017, taking extraordinarily detailed photographs of the planet and its moons, more than 1 hour passed between the moment a picture was taken and the moment that picture was received on Earth. Cassini would capture an image, turn it into digital data, transmit it as a radio signal moving at the speed of light, and over an hour later, that data would arrive at our antennas. Because of that delay, Cassini could not be flown, as if someone were joysticking it in real time. Engineers and scientists could not watch the live view and adjust the trajectory instantly, the way a pilot adjusts a plane or a person steers a drone. Instead, they had to compose detailed command sequences days or even weeks ahead of time, upload them to the spacecraft, and trust it to execute them properly. If a problem occurred, the probe needed sufficient onboard intelligence to recognize the issue and switch itself into a safe mode, because by the time a warning reached Earth and corrective instructions were sent back, more than 2 hours would have elapsed. The situation around the spacecraft could have changed drastically in that interval. 1 light day consists of 24 light hours, which is about 25,900,000,000 kilometers. At this scale, even the highest speeds humanity has achieved begin to look painfully slow. Voyager 1, the spacecraft launched in 1977 that currently holds the record for being the most distant human-made object from Earth, is roughly 24 light hours away as of the middle of the decade of the 2020s. It has been traveling for nearly 50 years at a speed of about 17 kilometers per second, which is around 61,200 kilometers per hour. That is incredibly fast by human standards. At that speed, you could cross an entire continent like the United States from coast to coast in only a couple of minutes. Yet even after almost 5 decades of continuous movement through the void, with essentially nothing to decelerate it, Voyager 1 still has not traveled a complete light day's distance from Earth. That span is approximately equal to the location of the heliopause, the frontier where the sun's direct influence terminates and true interstellar space commences. The heliopause represents the region where the solar wind, the relentless outward flow of charged particles radiating from the sun in every direction, finally weakens and blends with the interstellar medium, the sparse gas and dust that fill the void separating stars. Voyager 1 passed through this threshold in the year 2012, becoming the first human-built object to penetrate interstellar space. It was a historic accomplishment and a pivotal milestone in humanity's expansion into the universe. Nevertheless, it remains within 1 light day of the sun. In cosmic terms, it is still right here in our immediate vicinity. 1 light week equals 7 light days, roughly 181 billion kilometers. Now we are in territory where nothing created by humans has ever ventured, and nothing will for many decades or possibly centuries ahead. This is deep space, vastly beyond the planets, vastly beyond anything we have directly investigated. Out at this distance, the sun would no longer dominate as the overwhelming source of illumination and warmth it appears to be from Earth. It would appear as merely a brilliant star, certainly brighter than the others, but still just a point of light against the blackness. If you were somehow floating in space one light week from the sun, you would observe the sun as a radiant star. But you would also observe thousands of additional stars scattered across the dark expanse. You would understand, perhaps for the first time, that the sun is simply one star among countless others. One light month represents approximately 30 light days, around 778 billion kilometers. At this span, if you gazed back toward the sun through a telescope, you would perceive it as just another star, not significantly brighter than many others visible in the sky. The solar system, with all its planets and moons and asteroids and comets, would be barely discernible. Even with a sophisticated telescope, you might detect Jupiter as a faint speck, but the inner planets would be lost in the sun's radiance. Everything we consider the solar system, all the planets we have investigated and dispatched probes to, all the worlds we are familiar with, would be compressed into a minuscule region surrounding an unremarkable star. And 1 light year equals 365 light days. It is 12 light months. It is 52 light weeks. It is 8,760 light hours. It is 525,600 light minutes. It is 31,536,000 light seconds. Notice how rapidly the quantities escalate. We began with 1 light second, which was already an immense span by human measures, roughly the distance from Earth to the Moon and most of the return journey. And we have been multiplying by progressively larger factors: 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 7 days in a week, 30 days in a month, 12 months in a year. And we are only now arriving at 1 light year, 9.46 trillion kilometers. That is the span light covers in 1 year, traveling at 300,000 kilometers every single second for 365 days continuously. And this is the basic unit astronomers employ to express the separations between stars, because stars are separated by spans measured in light years. And nothing smaller is practical when you are working with these enormous cosmic scales. So why do astronomers rely on light years? Because every alternative is inferior. Imagine if astronomers used kilometers for all measurements. Proxima Centauri sits approximately 40,140 billion kilometers distant. That is cumbersome, difficult to retain in memory, and fails to convey any intuitive understanding of the span. But if I inform you that Proxima Centauri is 4.24 light years away, that is cleaner. You can make comparisons with other spans. Yet, if one star is 4 light years distant and another is 40 light years distant, you instantly recognize that the second is 10 times farther. Light years also connect distance and duration in a meaningful way. When you observe a star 4 light years distant, you are observing light that departed 4 years in the past. You are literally gazing into history. This relationship becomes essential when examining the universe. The velocity of light is not merely rapid. It is the maximum speed of the universe. Nothing can exceed it. And this is not a technical constraint that we might eventually overcome with superior engineering or more powerful propulsion systems. It is a fundamental principle of physics embedded in the actual structure of space-time itself. The velocity of light is not just a speed. It is a universal constant that determines the relationship between space, duration, energy, and matter. Einstein's theory of special relativity, released in 1905, demonstrated that as objects approach the velocity of light, extraordinary phenomena occur. These are not merely theoretical predictions. They are confirmed realities verified by innumerable experiments throughout the past century. Duration slows down for the moving object relative to stationary observers. This is termed time dilation, and it has been measured directly. The object's mass effectively increases, or more accurately, its inertia increases. It becomes progressively more difficult to accelerate. The quantity of energy necessary to accelerate it grows without limit as you approach light speed. To actually attain the velocity of light would demand infinite energy, which is impossible. The universe does not contain infinite energy. Consequently, nothing possessing mass can reach the velocity of light. Let me clarify why this occurs. In our everyday experience, if you are aboard a train traveling at 50 kilometers per hour and you throw a ball forward at 20 kilometers per hour relative to the train, someone standing on the platform would observe the ball traveling at 70 kilometers per hour. The velocities add together. This appears self-evident, and it functions perfectly well for ordinary speeds. But Einstein demonstrated that this straightforward addition fails when you are dealing with the velocities approaching the velocity of light. If you are aboard a spacecraft traveling at half the velocity of light and you activate a flashlight pointing forward, you might assume the light would travel at 1.5 times the velocity of light, at least from the viewpoint of someone observing you, but it does not. The light still travels at precisely the velocity of light, 300,000 kilometers per second, both from your viewpoint aboard the spacecraft and from the viewpoint of someone observing you from outside. This appears paradoxical. How can the light be traveling at the identical velocity for both observers when one observer is already traveling at half the velocity of light? The explanation is that space and duration adjust to maintain the velocity of light as constant. If you are traveling extremely fast, duration literally passes more slowly for you from the viewpoint of a stationary observer, and spans in the direction you are traveling actually compress. These are not optical illusions or measurement mistakes. They are genuine physical phenomena. Duration and space are not absolute. They are relative, dependent on your motion. The only thing that is absolute, that is identical for everyone regardless of how they are moving, is the velocity of light. This has been tested experimentally innumerable times. Particles in particle accelerators travel at velocities extremely close to the velocity of light. We can measure how long they survive before decaying, and we discover that particles traveling at 99.9% of the velocity of light survive much longer than identical particles at rest. Duration is literally passing more slowly for them. This is not theory, it is measured reality. GPS satellites orbiting Earth travel fast enough and are sufficiently distant from Earth's gravitational field that time dilation becomes measurable. The atomic clocks aboard GPS satellites operate at a slightly different rate than identical clocks on the surface. If GPS did not account for this time dilation phenomenon, your GPS navigation would be inaccurate by several kilometers within merely a few hours. The fact that GPS functions is evidence that time dilation is genuine. Cosmic rays, high-energy particles from space, generate muons when they collide with the upper atmosphere. Muons are subatomic particles that decay extremely rapidly, with a half-life of roughly 2 microseconds. At this rate, even traveling at nearly the velocity of light, muons generated in the upper atmosphere should not be capable of reaching the surface before decaying. And yet, we detect muons at ground level constantly. Why? Because from our viewpoint, the muons are traveling so rapidly that time dilation extends their lifespan. What represents 2 microseconds from the muon's viewpoint becomes significantly longer from our viewpoint, sufficiently long for them to reach the surface. Only massless particles like photons, which are particles of light, can travel at the velocity of light. Photons possess no rest mass, so they do not require infinite energy to attain light speed. In reality, photons must always travel at light speed. They cannot decelerate or accelerate. From the instant they are generated to the instant they are absorbed, they travel at precisely the velocity of light. No faster, no slower. This is simply what photons do. It is their fundamental nature. This has profound implications for space travel that extend beyond mere engineering obstacles. Even if we developed perfect propulsion systems with access to limitless energy, even if we resolved every engineering problem conceivable, we still could not travel faster than light. The 4.24 light years to Proxima Centauri represents a minimum travel duration of 4.24 years. Even in the most optimistic scenario, where we could somehow accelerate a spacecraft to nearly the velocity of light, and that is merely reaching the nearest star. Most destinations in space are vastly, vastly more distant. Some science fiction suggests methods around this constraint. Warp drives that distort space around a spacecraft, permitting it to effectively travel faster than light without actually moving faster than light through space. wormholes that generate shortcuts through spacetime connecting distant locations in space, hyperspace, an alternative dimension where the laws of physics are different and faster-than-light travel is achievable. These are imaginative concepts, and some, like warp drives, have a foundation in theoretical physics. The Alcubierre drive, proposed in 1994, is a theoretical solution to Einstein's field equations that would permit faster-than-light travel by contracting space ahead of a spacecraft and expanding it behind. There is no evidence whatsoever that any such thing exists or could possibly exist. As far as our knowledge extends, built upon over a century of rigorous experiments and observations, the velocity of light represents an absolute barrier. It is not an obstacle to be surmounted through superior technology. It is a fundamental law of nature. When we discuss a star's positioned hundreds or thousands of light years distant, we are discussing spans that might be fundamentally inaccessible with any technology that remains consistent with the laws of physics as we currently comprehend them. The light year does not merely quantify distance. It quantifies a barrier, a constraint, a frontier beyond which the ordinary principles of cause and effect begin to deteriorate. Let us discuss Proxima Centauri because it is our nearest stellar companion and helps us grasp these spans in practical terms. Understanding Proxima Centauri, the closest star beyond our Sun, provides us with a sense of what it signifies when we state that even the nearest stars are impossibly remote. Proxima Centauri is a small red dwarf star within the Alpha Centauri system, which is actually a triple star system. Two of them, Alpha Centauri A and B, are Sun-like stars orbiting each other. They are comparable in magnitude and luminosity to our Sun, and they orbit their mutual center of mass every 79.9 years in a slow gravitational dance that has continued for billions of years. If you could observe them at close range, Alpha Centauri A and B would resemble two suns circling each other against the darkness of space. Proxima Centauri is substantially smaller, roughly 1/8 the Sun's mass and 1/7 its diameter. It is so diminutive and faint that you cannot observe it with the unaided eye. Even though it is our nearest stellar companion, you require a telescope to locate it. Red dwarfs like Proxima Centauri are the most abundant type of star in the galaxy, comprising roughly 70% of all stars. But they are all so dim that none of them are visible to the unaided eye, despite being relatively numerous. When you gaze up at the night atmosphere, every star you can observe with your unaided eye is either larger and more luminous than the Sun, or it is not a star at all, but a planet. Proxima Centauri is 4.24 light-years distant, approximately 40,140,000,000,000 kilometers. That is 40 with 12 zeros following it. To position this in perspective, if you could somehow journey at the velocity of the fastest spacecraft humans have ever constructed, the Parker Solar Probe at 192 kilometers per second, it would require you roughly 6,800 years to arrive at Proxima Centauri. That is longer than the entirety of recorded human history. Writing was developed roughly 5,000 years ago. You could have commenced your voyage when humans first mastered writing, journeyed continuously at the fastest velocity any human spacecraft has ever attained, and you would still be journeying today, still thousands of years distant from your destination. There have been proposals for more rapid spacecraft. The Breakthrough Starshot Initiative, announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner, proposes utilizing powerful ground-based lasers to accelerate miniature spacecraft to roughly 20% of light velocity. The concept is elegant and scientifically sound, at least in principle. You construct a spacecraft that is essentially a computer chip with a camera weighing perhaps a gram attached to an ultra-thin light sail made of reflective material perhaps only a few atoms thick. Then you aim massive arrays of lasers at it from Earth. The laser light exerts pressure on the sail, and because the spacecraft is so incredibly light, it can be accelerated to tremendous velocities. At 20% of light velocity, which is roughly 60,000 kilometers per second, a probe could arrive at Proxima Centauri in approximately 20 years. Add another 4 years for signals to journey back to Earth at light velocity, and you could potentially obtain data from Proxima Centauri in 24 years from launch. That is within a human lifespan, which is exciting. You could initiate a mission when you are young and potentially witness the results before you die. But the engineering obstacles are enormous, perhaps insurmountable with current or near-future technology. First, you require incredibly powerful lasers. The proposal calls for a laser array with a total power of roughly 100 gigawatts. That is approximately the output of 100 nuclear power plants, all concentrated into a laser beam a few kilometers wide. This beam would need to track the tiny spacecraft as it accelerates, keeping the light precisely focused on the sail. Any deviation and the sail would drift out of the beam, and the acceleration would cease, leaving the spacecraft coasting at whatever velocity it had reached. Second, the spacecraft needs to survive the voyage. At 20% of light velocity, you are traveling at 60,000 kilometers per second. At this velocity, collisions with even minuscule particles become catastrophic. A speck of dust, something smaller than a grain of sand, striking the spacecraft at this velocity would release energy equivalent to a large bomb. The spacecraft would require shielding to protect it. But any shielding adds mass, and mass is the enemy when you are attempting to accelerate something with light pressure. The more the spacecraft weighs, the more power you require to accelerate it, and the equation deteriorates progressively as you add mass. Third, you need to be capable of communicating with the spacecraft across 4 light-years of distance. The tiny probe would require a laser or radio transmitter powerful enough to transmit data back to Earth from 4.24 light-years distant. At that distance, any signal disperses enormously. The power needed to transmit a detectable signal is substantial, and you have to incorporate this capability into a spacecraft the size of a computer chip. It is like attempting to shout across an ocean and be heard clearly on the opposite side. Fourth, you need to actually target Proxima Centauri's star system and fly past it at the correct distance and angle to obtain useful data. At 20% of light velocity, the spacecraft is traveling so rapidly that it crosses the orbit of Mars in roughly 40 minutes. The entire width of our solar system from the Sun to Neptune is crossed in approximately 6 hours. You get one opportunity. There is no decelerating, no course adjustments once you are up to velocity, because decelerating would require just as much energy as accelerating, and you do not have that energy available in a spacecraft weighing a gram. The spacecraft flies past Proxima Centauri at 60,000 kilometers per second, has perhaps a few hours, or at most a few days, when it is proximate enough to capture useful images and measurements, and then continues onward into the void, never to be encountered again, drifting through interstellar space eternally. So while Breakthrough Starshot is an intriguing concept, and it is founded on actual physics rather than science fiction, it remains highly theoretical. The technology does not exist yet, and there are formidable challenges that might be impossible to overcome. Even if we somehow constructed such a craft and successfully dispatched it tomorrow, it would be at least 20 years before it reached Proxima Centauri, and another 4 years before we obtained any data back. That is a 24-year round trip for information, assuming everything functions perfectly, which in the history of space exploration has never been a safe assumption. And this is merely to reach our nearest stellar companion, the closest star to our Sun. With technology we can actually construct today, the kind of spacecraft we understand how to engineer and launch with current rockets and current materials and current computer systems, reaching Proxima Centauri would require not decades, but millennia. We would need to construct multi-generational spacecraft, massive vessels that could sustain human crews for thousands of years. The people who arrived at Proxima Centauri would be the distant descendants of those who launched, perhaps hundreds of generations removed, living in a world they had never departed, journeying to a destination they had only heard about in stories transmitted through the centuries. When you gaze up at the night atmosphere, you are observing stars at various distances, and you are observing them as they existed years or even centuries in the past. This is one of the most profound implications of the light year. Distance and duration become inseparable. You cannot separate where something is located from when you are observing it. Light travels at a finite velocity. It is incredibly rapid, but it is not instantaneous. When light departs a star and travels through space toward Earth, that voyage requires duration. And during that duration, circumstances can change. The star might alter in brightness. It might change color. It might explode. By the time the light reaches your eyes, the star you are observing might be completely different from how it exists right now. Or it might not even exist anymore. Sirius, the most luminous star in the night atmosphere, is 8.6 light-years distant. When you observe Sirius tonight, you are observing light that departed that star 8.6 years ago. You are observing Sirius as it existed when you were 8.6 years younger. If you are 20 years old, you are observing Sirius as it existed when you were approximately 11, probably in middle school. If you are 40, you are observing it as it existed when you were in your early 30s. The Sirius you observe tonight is Sirius from the past, not Sirius as it exists right now in this present moment. Now, Sirius is a stable main sequence star. It is not going to change substantially over a few years or even a few decades. In 8.6 years, Sirius does not age noticeably. Stars transform very gradually from a human perspective over millions or billions of years rather than years or decades. But the principle is what matters here. You are not observing Sirius as it is. You are observing Sirius as it was. You are gazing back in duration every time you observe a star. Vega is another luminous star, roughly 25 light-years distant. If you are 25 years old and you observe Vega tonight, you are observing light that departed that star the year you were born. When that light commenced its voyage toward Earth, you had not been born yet. You did not exist. Your parents might have been gazing up at that same star, observing light that departed Vega 25 years before that, 50 years ago total. The Vega you observe tonight is a younger Vega, showing you what that star resembled a quarter-century ago, not as it exists right now. Betelgeuse, the red supergiant in the constellation Orion, is roughly 550 light-years distant. It is one of the most famous stars in the night atmosphere, easily visible as the bright reddish star marking Orion's shoulder. The light you observe from Betelgeuse tonight commenced its voyage toward Earth in the year 1474, during the Italian Renaissance, before Columbus sailed to the Americas, when Leonardo da Vinci was 22 years old and Michelangelo was about to be born. In 1474, the Byzantine Empire had fallen to the Ottoman Turks 21 years earlier. The printing press had been invented only roughly 20 years before. Most of Europe was still emerging from the Middle Ages. The modern world as we know it did not exist yet, and the light from Betelgeuse that you observe tonight commenced its voyage back then. It has been traveling through space for over 500 years, crossing the vast darkness between Betelgeuse and Earth to arrive at your eye tonight. Betelgeuse is a particularly interesting example because it is a massive star nearing the conclusion of its existence. Stars like Betelgeuse do not endure as long as smaller stars like the Sun. They consume their fuel much more rapidly. At some point in the relatively near future, astronomically speaking, within the next 100,000 years or so, Betelgeuse will explode as a supernova. When it does, it will briefly shine as brilliantly as the full moon in our atmosphere, visible even during the day. It will be a spectacular occurrence, one of the most dramatic astronomical events visible from Earth in human history. However, here is the reality. Betelgeuse might have already detonated. The explosion might have taken place centuries in the past. Perhaps it took place in the year 1600, or 1700, or 1800. But we would not be aware yet. We would possess no means of knowing. The light from that explosion would still be journeying toward us through space, moving at the velocity of light, requiring 550 years to complete the voyage. So if Betelgeuse detonated in the year 1700, we will not witness it until approximately the year 2250. The star could already be destroyed right now, obliterated in a catastrophic supernova explosion, and we would still witness it shining peacefully in the sky for centuries to come, completely oblivious that we are witnessing a phantom, an image of something that no longer has existence. Polaris, the North Star, is approximately 445 light-years distant. When its current light commenced journeying toward us, the first permanent English colonies in North America had not been established yet. Jamestown would not be founded for another 12 years. The Pilgrims would not arrive at Plymouth Rock for another 26 years. William Shakespeare had only just begun composing his plays. He had written some of his early works, but had not yet written Hamlet, Macbeth, King Lear, or most of his other celebrated plays. The United States would not exist for another 180 years. When that light from Polaris commenced its voyage, the world was fundamentally different from today. And tonight, that ancient light enters your eye. You are connected across space and duration by photons that have been journeying for 4.5 centuries. Within approximately 20 light years of Earth, there are roughly 130 known star systems. Some are solitary stars like our Sun. Others are binary systems with 2 stars orbiting each other, or even triple star systems like Alpha Centauri. Understanding this stellar neighborhood helps us appreciate both the spans involved and the variety of stars that exist in our cosmic vicinity. Barnard's star is the second nearest star system to Earth after Alpha Centauri, approximately 6 light-years distant. It is a red dwarf, substantially smaller and fainter than the Sun. What makes Barnard's star particularly intriguing is that it is moving toward us relatively rapidly by stellar standards. It possesses the largest proper motion of any known star, meaning it moves across the sky more rapidly than any other star as observed from Earth. Over the course of decades and centuries, we can actually observe Barnard's star change position relative to other stars. In approximately 10,000 years, it will be nearer to Earth than Proxima Centauri is now, becoming our new nearest stellar companion. But even at its closest approach, it will still be nearly 4 light-years distant. The spans between stars are so immense that even when stars are moving toward each other, it requires thousands or tens of thousands of years for that motion to produce a noticeable difference in the distance separating them. Wolf 359, approximately 7.9 light-years distant, is one of the fastest moving stars relative to the Sun, traveling at roughly 119 kilometers per second. That is rapid by stellar standards. Most stars in our region of the galaxy move at velocities of a few tens of kilometers per second relative to each other. Wolf 359 is moving substantially faster. Yet even at this velocity, it is moving at only approximately 0.04% of the velocity of light. Stars move, but they move gradually compared to the vast spans between them. Even the fastest moving nearby star would require tens of thousands of years to traverse a light year. Sirius, 8.6 light-years distant, is actually a binary system with 2 stars orbiting each other. Sirius A is a brilliant white main sequence star, approximately twice the mass of the Sun. It is the most luminous star in our night sky, partly because it is relatively proximate, and partly because it is intrinsically quite luminous. Sirius B is completely different. It is a white dwarf, the dense remnant of a star that exhausted its nuclear fuel and collapsed. White dwarfs are fascinating objects. They are roughly the size of Earth, but possess the mass of a star. Sirius B has approximately the mass of our Sun, compressed into a sphere roughly the size of our planet. This renders it incredibly dense. A teaspoon of material from Sirius B would weigh roughly 5 tons on Earth. The 2 stars orbit each other every 50 years, locked together by gravity, each following an elliptical path around their mutual center of mass. The Milky Way is a spiral galaxy containing between 100 billion and 400 billion stars. That is a substantial range because it is actually quite difficult to count stars in our own galaxy. We are inside it, like attempting to count trees while standing in the middle of a forest. Dust obstructs our view in many directions. Dim stars are difficult to detect, and the galaxy is so enormous that we cannot observe all of it at once from our position. But the best estimate suggests somewhere between 100 billion and 400 billion stars, with the most probable number being around 200 to 300 billion. Our Sun is merely one of these stars, an ordinary yellow dwarf star of average magnitude and luminosity. There is nothing exceptional about our Sun from a galactic perspective. It is not the largest, not the most luminous, not the hottest, not the coolest. It is simply a typical star, one among hundreds of billions. And it is positioned in one of the spiral arms approximately 26,000 light-years from the galactic center. 26,000 light-years. The light we observe from the center of our galaxy, if we could see through all the dust obstructing the view, departed the galactic center 26,000 years ago. When that light commenced its voyage, humans were still living as hunter-gatherers in the Stone Age. Agriculture had not been developed yet. There were no permanent settlements, no cities, no civilization as we comprehend it. People lived in small nomadic groups, following animal herds, gathering wild plants, utilizing simple stone tools. Writing would not be developed for another 21,000 years. Everything we consider human civilization, Everything from the first farms to the first cities, to the first writing, to all the ancient empires to the modern world. All of it has transpired while light from the galactic center was journeying toward us. And that light, which departed when humans were still primitive hunter-gatherers, arrives at Earth tonight. The Milky Way is approximately 100,000 light years across from one edge of the spiral arms to the other. If you could somehow journey at the velocity of light, which you cannot, it would require you 100,000 years to cross the galaxy from one side to the other. 100,000 years. Modern humans, Homo sapiens, are roughly 300,000 years old as a species. So you could have commenced crossing the galaxy when the first modern humans appeared in Africa, journeyed at the velocity of light for 100,000 years, and you would only be 1/3 of the way across the galaxy today. The Sun orbits the galactic center at a velocity of approximately 230 kilometers per second. That sounds rapid, and it is rapid. At that velocity, you could journey across the United States in roughly 3 minutes. You could circle Earth in just under 3 minutes. But even at this remarkable velocity, it requires the Sun approximately 225 million to 250 million years to complete one orbit around the galaxy. The last time the Sun was in its current position in the galaxy, dinosaurs were only beginning to develop on Earth. The first dinosaurs appeared roughly 230 million years ago. Since then, the dinosaurs developed, dominated Earth for over 160 million years, went extinct 66 million years ago, mammals assumed dominance, and humans eventually developed, and the Sun has only just now returned to approximately the same position in the galaxy, where it was when dinosaurs first appeared. One of the most exciting developments in astronomy over the past few decades has been the discovery of exoplanets, planets orbiting stars other than our Sun. Until 1992, we possessed knowledge of only one planetary system, our own solar system, with its 8 planets orbiting the Sun. We suspected other stars might possess planets, but we had no direct evidence. Then, in 1992, astronomers detected the first planets orbiting another star, a pulsar. In 1995, they found the first exoplanet orbiting a normal Sun-like star. And since then, the discoveries have exploded. As of 2024, we have confirmed the existence of over 5,000 exoplanets, with thousands more candidates awaiting verification. The TRAPPIST-1 system, approximately 40 light-years distant, contains 7 Earth-sized planets orbiting a small red dwarf star. 3 of these planets are in the habitable zone, where temperatures could potentially permit liquid water to exist on the surface. This discovery, announced in 2017, was revolutionary for several reasons. It demonstrated that small red dwarf stars can host multiple rocky planets. Since red dwarfs are the most common type of star in the galaxy, comprising approximately 70% of all stars, this suggests rocky planets might be extremely common throughout the universe. The TRAPPIST-1 system is also remarkable because the planets are packed tightly together. All 7 planets orbit nearer to their star than Mercury orbits our Sun. But because the star is so small and cool, 3 of the planets receive approximately the same quantity of energy from their star as Earth receives from the Sun. If you stood on one of these planets, you would observe the other planets in the sky. Some appearing larger than our Moon appears from Earth. The planets are so proximate together that travel between them would be far easier than travel between planets in our solar system. When we observe the TRAPPIST-1 system today, we are observing it as it existed 40 years ago, in 1985. If there is intelligent life on one of those planets, and if that life developed radio technology and commenced broadcasting signals into space, those signals would require 40 years to reach us. We would be receiving signals today that were broadcast in 1985. And if we detected such a signal today and transmitted a response, it would require another 40 years for our response to reach them. They would receive our reply in 2065. That is an 80-year round trip for a single exchange of information. You could pose a question and die of old age before receiving an answer. Let us consider what communication signifies when distances are measured in light years. This is one of the most challenging and sobering aspects of the scale of space, and it possesses profound implications for any future where humanity might attempt to establish settlements on other worlds or make contact with alien civilizations. Radio waves journey at the velocity of light. They are electromagnetic radiation, just like visible light, but with longer wavelengths. When we transmit radio signals into space, they propagate outward in all directions at 300,000 kilometers per second. But even at this remarkable velocity, the fastest velocity possible in the universe, communication across light years requires years. Voyager 1, our most distant spacecraft, is now approximately 24 light hours distant from Earth. That signifies there is a communication delay of roughly 24 hours each direction. When mission controllers on Earth transmit a command to Voyager, that command requires approximately 24 hours to reach the spacecraft. The radio signal journeys at light velocity, covering roughly 25 billion kilometers to reach Voyager. Any data Voyager transmits back requires another 24 hours to reach Earth. There is approximately a 48-hour delay for any two-way communication. If something malfunctions with the spacecraft, if a system fails or an anomaly occurs, Voyager must handle it autonomously. By the time engineers on Earth become aware there is a problem and transmit new commands to address it, 2 full days have elapsed. The situation could have transformed completely in that duration. The New Horizons spacecraft, which flew past Pluto in July 2015, was approximately 4.5 light hours distant from Earth during the flyby. All the data it collected during those few precious hours near Pluto had to be stored aboard the spacecraft, then transmitted back to Earth over the following months. Every command sequence had to be programmed weeks or months in advance. Mission controllers could not react to what the spacecraft was observing in real time. They had to plan everything perfectly, anticipate every possible scenario, and trust that the spacecraft would execute its mission autonomously. Now, imagine attempting to establish communication with a human settlement on a planet orbiting Proxima Centauri, 4.24 light-years distant. You transmit a message inquiring how circumstances are progressing, how the crops are developing, whether there are any difficulties that need addressing. That message journeys at light velocity for 4.24 years. 4 years, 2 months, and approximately 20 days later, your message arrives. If they respond immediately, composing their response and transmitting it right back, their answer requires another 4.24 years to reach you. That is over 8 years for a single exchange of information. You could inquire about their latest harvest and receive an answer about crops that were consumed 4 years ago. You could inquire how a sick person is faring and receive news of their death years after it occurred. You could transmit advice or assistance, but by the time it arrives, the situation will have transformed completely. Any kind of immediate communication, the kind of instantaneous back and forth conversation we take for granted, is completely impossible across these distances. Conversations would be painfully, frustratingly gradual. Debates would span decades. A diplomatic negotiation between Earth and a Proxima colony could require a century or more to resolve, with each party having to carefully contemplate their responses, knowing that years would elapse before hearing back and years more before their reply could be answered. This has profound implications for governance and society that extend far beyond mere inconvenience. A colony 4 light-years distant could not be governed from Earth in any meaningful sense. Any laws or directives transmitted from Earth would arrive years out of date. The political situation on Earth could transform completely between when a message was transmitted and when it arrived. By the time the colony receives orders from Earth, those orders might be obsolete, overturned by new governments or new policies. The colony would need to be autonomous, capable of making its own decisions on everything from resource allocation to conflict resolution to emergency response, because waiting years for approval or guidance on every decision would be impossible. The colony and Earth would drift apart culturally over time, developing their own customs, their own ways of life, their own solutions to problems. They would be connected by messages from the past, letters from another era, but unable to maintain the kind of immediate ongoing connection that holds societies together. Over generations, they might become so different that they would barely recognize each other anymore. They would share a common origin, a common history up to the point of separation. But from that point forward, they diverge, evolving separately like species isolated on different islands. For more distant stars, it becomes even worse. A settlement 10 light-years distant would have a 20-year round-trip communication time. Messages you transmit to your children living there would reach them when they are adults, possibly with children of their own. Their responses would return when your grandchildren are grown, when you are elderly, or possibly deceased. You would exchange letters across the decades like messages from different eras. You could share news and stay in contact in some abstract sense, but you could not have a relationship in any normal meaning of the term. A civilization 100 light years distant would have a 200-year communication delay. You could transmit a message, and neither you nor your children, nor your grandchildren, nor even your great-grandchildren would live to witness the reply. Only your great-great-great-grandchildren, living in a world you could barely imagine, might hear back from the distant civilization. The conversation would span generations, each generation transmitting messages to strangers they would never meet. People separated not just by distance, but by duration, receiving messages from people long deceased. If you could journey close to light velocity, something extraordinary happens with time. This is Einstein's time dilation, and it has been confirmed by countless experiments. It is not speculation or theory in the sense of being unproven. It is observed reality as solidly established as gravity or electromagnetism. As you approach light velocity, duration slows down for you relative to stationary observers. The faster you travel, the more extreme this becomes. This is not just clocks operating slowly. This is duration itself passing more slowly. Your heartbeat, your thoughts, your aging, your metabolism, everything happens more slowly from the perspective of someone who is not moving with you. Though from your perspective, sitting in your spacecraft, everything appears normal. Duration passes normally for you. It is everyone else's duration that seems to be passing rapidly. Imagine a spacecraft that could somehow reach 99.9% of light velocity. Not quite light velocity, but extremely close. You board this spacecraft and journey to a star 10 light years distant, then turn around and return. From Earth's perspective, this voyage requires approximately 20 years. 10.1 years to arrive there at 99.9% of light velocity and another 10.1 years to return. Anyone observing from Earth would witness your spacecraft require approximately 20 years for the round trip. But because of time dilation, you would age substantially less. At 99.9% of light velocity, duration passes approximately 22 times slower for you than for people on Earth. So while 20 years elapsed on Earth, you would only experience an age approximately 11 months. You would disembark from the spacecraft having aged less than a year, while everyone you knew aged 20 years. Your younger sibling might now be older than you. Your children, if you had any, might now be adults older than you. You have traveled into their future. If you traveled even faster, at 99.99% of light velocity, you could journey to a star 100 light years distant and back. From Earth's perspective, this voyage requires over 200 years. But from your perspective, due to extreme time dilation at this velocity, the voyage might require only a few years of your life. You would experience a few years of travel duration, living through a few years aboard the spacecraft. But when you return to Earth, over 200 years would have elapsed. Everyone you knew would be long deceased. The world would be completely different. Political systems would have transformed. Technologies would have advanced. Languages might have evolved. You would return to a future Earth that would be as foreign to you as if you had traveled forward in duration. Let us zoom out even further. The observable universe is the region of space from which light has had duration to reach us since the Big Bang. The universe is approximately 13.8 billion years old. Light has been journeying toward us for all that duration, but the observable universe is larger than 13.8 billion light years because the universe has been expanding while the light was journeying toward us. The observable universe is approximately 46.5 billion light years in radius, making it approximately 93 billion light years across. This is the distance to the edge of what we can possibly observe. Beyond this distance, space has been expanding so rapidly that light from those regions has not reached us yet and never will. There is a cosmic horizon beyond which we cannot observe, not because we do not possess powerful enough telescopes, but because the light simply has not had duration to reach us yet, given the age of the universe and the rate of expansion. Within this observable universe are an estimated 2 trillion galaxies. Each galaxy contains billions or trillions of stars. If you multiply it out, the total number of stars in the observable universe is estimated at around 200 billion trillion. That is a 2 followed by 23 zeros. And we know from observations that most stars possess at least one planet orbiting them. So there are probably similar quantities of planets, perhaps even more. The universe is filled with worlds, more worlds than we could ever count, more worlds than we could ever visit, even if we possessed unlimited duration and unlimited technology. At the largest scales, the universe possesses structure. Galaxies are not randomly scattered through space like grains of sand. They are organized into clusters, groups of galaxies held together by gravity. These clusters are organized into superclusters, massive structures containing multiple galaxy clusters. And the superclusters are arranged in filaments, enormous thread-like structures stretching hundreds of millions of light years across space. Between these filaments are vast voids, regions with very few galaxies, empty spaces that can be hundreds of millions of light years across. The universe is expanding. Space itself is stretching, carrying galaxies with it like raisins in rising bread dough. This is not merely galaxies moving through space. Space itself is expanding, creating more space between distant objects. For nearby objects, this expansion is negligible, overwhelmed by other forces. The space between Earth and the Moon is not expanding in any meaningful manner. Gravity holds Earth and Moon together. The space within our solar system is not expanding. Gravity holds the planets in their orbits. The space within our galaxy is not expanding. Gravity holds the stars together in the Milky Way. But on larger scales, between galaxies, and especially between galaxy clusters, separated by hundreds of millions or billions of light years, the expansion becomes significant and eventually dominant. Distant galaxies are receding from us as space expands between us and them. The farther distant a galaxy is, the faster it is receding. This is not because the galaxies themselves are moving through space at high velocities. They are sitting relatively stationary in their local regions of space, but the space between us and them is expanding, and the cumulative expansion over vast distances accumulates to high recession velocities. For galaxies that are sufficiently distant, space between us and them is expanding more rapidly than light can journey through it. This does not violate the cosmic velocity limit because the galaxies themselves are not moving faster than light through space. They are essentially stationary in their local space, but the space itself is expanding so rapidly that the distance between us increases faster than light could traverse it. It is like attempting to walk on a treadmill that is moving backward more rapidly than you can walk forward. You are walking at your normal velocity, but you are moving backward relative to your starting point because the treadmill is moving faster than your walking velocity. This signifies there are regions of the universe that are moving away from us so rapidly that light from those regions will never reach us, ever. Not in a billion years, not in a trillion years, not ever. There is a cosmic horizon beyond which we cannot observe, not because the light has not had duration to reach us yet, but because it never will reach us. The expansion of space is carrying those regions away more rapidly than light can close the gap. We are fundamentally, irreversibly cut off from those regions of the universe. Given the vast quantity of stars and planets, given that the universe is 13.8 billion years old, given that life arose on Earth relatively rapidly after conditions became suitable, it seems probable that life should exist elsewhere, perhaps even intelligent technological life. And yet, we have never detected any signs of alien civilizations. No radio signals carrying messages, or even just the electromagnetic noise of alien technology. No laser pulses, no megastructures, no signs of large-scale engineering projects, nothing. The universe appears to be silent. This is called the Fermi Paradox, named after physicist Enrico Fermi, who famously inquired, "Where is everybody?" The light year might be part of the answer. The distances between stars are so immense that they present enormous, perhaps insurmountable barriers to communication and travel. Our radio signals, our television broadcasts, our radar installations have been leaking into space for approximately a century now. These signals journey at light velocity, spreading outward in an expanding sphere. They have now reached all stars within approximately 100 light years of Earth. That sounds like a lot. 100 light years is a huge distance by human standards, but the Milky Way galaxy is 100,000 light years across. Our signals have covered a sphere 100 light years in radius, in a galaxy 100,000 light years across. That is a minuscule fraction of the galaxy. We have barely announced our presence to our immediate cosmic neighborhood, and even those signals are becoming weaker as they spread out. The farther they journey, the more they disperse, spreading out over a larger and larger sphere. By the time our television broadcasts reach a star a few dozen light years distant, they are so faint they would be almost impossible to detect above the background noise of space. Even with very sensitive equipment, any alien civilization attempting to detect us would require extremely powerful radio telescopes pointed in our exact direction, at the right frequency, at the right moment to pick up our signals. So what does all this signify for us? How should we think about light years in our daily existence? For most people, light years do not affect daily existence at all. You do not need to contemplate Proxima Centauri being 4.24 light years distant when you are deciding what to have for breakfast, whether to take an umbrella, or which route to take to work. But there is value in occasionally stepping back and contemplating these scales. It provides perspective on our place in the universe. When you comprehend that Earth is a small planet orbiting an ordinary star, and that the nearest other star is over 4 light years distant, and that our galaxy contains hundreds of billions of stars, and that there are trillions of galaxies in the observable universe, it transforms how you perceive things. Your problems, whatever they are, exist on a tiny planet in a vast universe. That argument with a friend, that stress at work, that anxiety about the future, that disappointment, that frustration, all of it happens on one small world. The nearest star does not care about your problems. The galaxy does not notice. The universe continues its slow evolution, completely indifferent to human affairs. This is not meant to diminish your experiences or suggest your problems do not matter. Your existence matters to you, and that is what is important. Pain is pain. Joy is joy. Love is love. These things are real and important, regardless of the scale of the universe. But sometimes when circumstances feel overwhelming, when you are stressed or anxious or worried, it can help to remember the scale of the universe. It can help to remember that you are living on a small planet orbiting an ordinary star in a vast cosmos. And that from that cosmic perspective, your problems are temporary, local, small. Not unimportant, but small, contained, manageable. There is also something beautiful about understanding light years. When you gaze up at the night sky, you are not merely observing points of light. You are observing stars that are light years distant. You are observing photons that have been journeying through space for years or centuries to reach your eyes. You are connected to those distant suns across vast distances of space and duration. You are part of the universe, made of atoms forged in stars, gazing up at other stars, understanding your place in the cosmic order. Every star possesses a story. Some are young, just forming from collapsing clouds of gas and dust, commencing their lives as nuclear furnaces. Some are middle-aged, like our sun, steadily burning hydrogen in their cores, stable and long-lived. Some are old, approaching the conclusion of their existence, having exhausted their fuel, destined to become white dwarfs cooling slowly over trillions of years, or to explode as supernovae, scattering their atoms across space to be recycled into new stars and planets. And all of them are separated by light years, by distances so immense that even light requires years to cross them. The universe is a sparse place, with tiny islands of light separated by enormous oceans of darkness. And yet those islands are connected. Connected by light, connected by gravity, connected by the fact that they are all made of the same material. Atoms forged in the hearts of earlier stars, scattered and recycled and reformed into new generations of stars and planets and potentially life. As our technology improves, our ability to measure distances in light years becomes more precise. The Gaia spacecraft is creating the most precise three-dimensional map of our galaxy ever made. It is measuring positions and distances of over 1 billion stars. Future telescopes will allow us to observe even farther. James Webb is already detecting galaxies over 13 billion light-years distant. Future observatories might observe even farther back, closer to the Big Bang. We are also discovering more exoplanets every year. As of 2024, we have confirmed over 5,000 exoplanets, with thousands more candidates. Many are dozens or hundreds of light-years distant. We are mapping what exists at these vast distances. In the future, we might dispatch robotic probes to nearby stars. Breakthrough Starshot proposes transmitting tiny spacecraft to Proxima Centauri. Even if successful, probes would require over 4 years to transmit back data. But barring revolutionary breakthroughs in physics, light years will remain a fundamental barrier. The distances between stars are vast, and light velocity is finite. This is not a problem to be resolved. It is a fundamental property of the universe we inhabit. Understanding light years transforms how we perceive our place in the universe, and it raises profound questions about the future of humanity and our relationship with the cosmos. These are not merely abstract philosophical questions. They possess real implications for how we think about space exploration, the search for life, and the long-term future of our species. For most of human history, the universe was small. Ancient people thought the stars were lights attached to a celestial sphere just beyond the moon and planets. The entire cosmos was contained within a space you could reach if you climbed high enough. Even when we comprehended the stars were distant suns, we possessed no sense of how distant they genuinely were. A few million kilometers, a few billion. The numbers were beyond our ability to measure, so they remained abstract, undefined. It was not until the early 20th century that we commenced accurately measuring the distances to stars and comprehending just how vast space genuinely is. When Harlow Shapley calculated the size of the Milky Way in 1918, demonstrating it was approximately 100,000 light-years across, many astronomers were shocked. The universe was far larger than anyone had imagined. And when Edwin Hubble demonstrated in 1929 that the spiral nebulae were actually distant galaxies, millions of light-years distant, the universe suddenly expanded again by orders of magnitude. We transitioned from thinking the Milky Way was the entire universe to comprehending it was merely one galaxy among potentially billions. Today, we possess knowledge that the observable universe is 93 billion light-years across and contains approximately 2 trillion galaxies. That is a number so enormous, it is almost meaningless. But it represents a real physical space that exists all around us. Every direction you observe, if you could observe far enough, you would witness galaxies stretching away into the distance. More and more galaxies, until finally you would reach the edge of the observable universe, where the light simply has not had duration to reach us yet. This knowledge transforms our perspective in fundamental ways. We are not at the center of the universe. We are not exceptional in any cosmic sense. We inhabit a typical planet orbiting a typical star in a typical galaxy, in a typical region of space. There is nothing unique about our location. If you were transported to another galaxy billions of light-years distant, you would witness a similar view. Galaxies in every direction, stretching away to the horizon. The universe appears roughly the same from every vantage point. This is both humbling and empowering. Humbling because it demonstrates how insignificant we are in cosmic terms. The entire history of human civilization, everything we have ever accomplished, every conflict fought, every empire constructed, every discovery made, all of it has occurred on one small planet, in one small corner of one typical galaxy. From a cosmic perspective, we barely register. We are like bacteria inhabiting a drop of water, completely unaware of the ocean that surrounds us. But it is also empowering because it demonstrates what we are capable of. We figured this out. We measured these distances. We comprehended our place in the cosmos. We constructed telescopes and spacecraft and mathematical models that permitted us to observe and measure things billions of light-years distant. We are tiny, but we are also incredibly capable. We are conscious beings who can comprehend the universe that created us. That is remarkable. Understanding light years forces us to confront difficult truths about space exploration and the future of humanity beyond Earth. The distances involved are so immense that they might represent fundamental barriers that no quantity of technological advancement can overcome. Consider what it would require to dispatch humans to another star. Proxima Centauri is 4.24 light-years distant. With current technology, the fastest spacecraft we have constructed travels at approximately 192 kilometers per second at its peak. At that velocity, it would require approximately 6,800 years to reach Proxima Centauri. That is longer than all of recorded human history. You could have launched your mission when humans first developed writing, and it still would not have arrived yet. To make interstellar travel practical, we would need to travel substantially faster, even at 10% of light velocity, which would require revolutionary new propulsion systems far beyond anything we can currently construct. It would still require over 42 years to reach Proxima Centauri. That is longer than most careers, longer than the typical span from graduation to retirement. And that is merely to reach the nearest star. Most stars are substantially more distant. The engineering challenges are formidable. You require enormous quantities of energy to accelerate a spacecraft to these velocities. You require protection for the crew from radiation during the voyage. You require life support for decades. You require dealing with the psychological effects of being confined in a small spacecraft for most of your existence, never observing Earth again, journeying through empty space toward a destination you might not reach in your lifetime. Multi-generational ships have been proposed, massive vessels that could sustain hundreds or thousands of people for the centuries it would require to reach another star. The people who arrive would be the distant descendants of those who launched. They would have been born on the ship, lived their entire existence on the ship, and would finally arrive at a destination they had only heard about in stories. The ship would effectively be a small, moving civilization, cut off from Earth, evolving its own culture and society during the long voyage. But even multi-generational ships might not be practical. How do you maintain a closed ecosystem for centuries? How do you prevent genetic problems from inbreeding in a small population? How do you ensure the descendants still desired to complete the mission their ancestors initiated? What if they decide several generations in that they wish to turn around and return home? What if there is a disaster, a system failure, a plague that eliminates most of the population? There is no rescue coming. They are light years from assistance. Some have proposed suspended animation or cryogenic freezing, putting the crew to sleep for the voyage and awakening them when they arrive. This would resolve many problems. No need for decades of life support, no psychological issues from long confinement, no generational drift in mission objectives. But we do not know if such technology is even possible. Can human bodies survive being frozen for decades or centuries and then revived? What about cellular damage from ice crystal formation? What about the effects on the brain and memory? These are all unsolved problems that might not possess solutions. The reality is that interstellar travel with humans aboard might simply be impractical, given the constraints imposed by the velocity of light and the vast distances measured in light years. We might be confined to our own solar system for the foreseeable future, perhaps permanently. That does not signify we cannot explore other star systems with robotic probes, but human exploration of other stars might remain forever in the realm of science fiction. The light year also shapes our thinking about the possibility of contact with alien civilizations. If intelligent life exists elsewhere in the universe, and many scientists think it probably does given the vast quantity of stars and planets, the distances measured in light years might make contact impossible even if both civilizations survive for millions of years. Let us say there is an advanced technological civilization on a planet orbiting a star 50 light years distant. They have developed radio technology and have been broadcasting signals into space for a century, just like we have. Those signals are now passing through our region of space, but they are incredibly faint after traveling 50 light years, spreading out over an enormous sphere. To detect them, we would require pointing very sensitive radio telescopes in exactly the right direction, at exactly the right frequency, at exactly the right moment. The chances of that happening by accident are incredibly small. Even if we did detect their signals, consider what happens next. We would be receiving signals they broadcast 50 years ago. If we responded immediately, our response would require another 50 years to reach them. That is a 100-year round trip for a single exchange. You could pose a question and die of old age before receiving an answer. Your grandchildren might hear the response to a question you posed. This fundamentally transforms the nature of any potential contact. There can be no dialogue in any normal sense, no conversation, no negotiation in real time. Instead, it would be more like an exchange of encyclopedia entries. Each civilization transmits everything they know, everything about their history and science and culture, and hopes the other civilization receives it and responds similarly. It would be more like archaeology than communication, studying the records left by a distant civilization, records that are decades or centuries old by the time they arrive. And that assumes both civilizations survive long enough and remain interested in communication long enough for this exchange to occur. Humans have only been broadcasting radio signals for approximately a century. We do not know if we will still be broadcasting in another century, let alone several centuries. Civilizations might rise and fall on timescales shorter than the light travel duration between stars. We might detect signals from a civilization that went extinct centuries ago, listening to the radio echoes of a deceased world. There is also the disturbing possibility that the universe might be full of civilizations, but they are all so distant that none of them ever make contact. The average distance between intelligent civilizations might be thousands of light years. At such distances, even detecting each other becomes nearly impossible, and communication becomes pointless. Each civilization develops alone, makes its discoveries alone, poses its questions alone, and eventually dies alone, never knowing if anyone else was out there. One of the most profound implications of understanding light years is the realization of just how isolated we are. The distances between stars are so immense that meaningful contact or travel might simply be impossible, leaving civilizations forever isolated in their own small regions of space. Even within our own galaxy, even assuming there are millions of technological civilizations, the average distance between them might be thousands of light years. At such distances, communication becomes almost pointless. By the time you receive a message and transmit a response, thousands of years have elapsed. The civilization that transmitted the original message might not even exist anymore. Their planet might have been destroyed by an asteroid impact, or they might have destroyed themselves in a conflict, or their star might have become unstable and rendered their world uninhabitable. You would be transmitting a message to phantoms. This creates a picture of a universe that might be full of life, perhaps even intelligent life, but where that life is forever isolated by the vast distances of space. Each civilization develops alone, poses its questions alone, makes its discoveries alone, and eventually dies alone, never knowing if anyone else was out there, never making contact with other minds under other suns. There is something melancholy about this. We have evolved as social creatures. Connection with others is fundamental to who we are as humans. We build communities, share knowledge, collaborate on projects. The idea of being alone in the universe, or of being surrounded by others but forever unable to reach them, or communicate with them meaningfully, is profoundly isolating. But there is also something beautiful about it. It signifies every civilization that does arise is precious. If we are alone, or effectively alone because we cannot reach anyone else, then we carry a unique responsibility. We are the universe's way of knowing itself in this particular corner of space. The thoughts we think, the art we create, the science we discover, the love we feel, all of it is unique to us. We are not merely one civilization among millions. We might be the only minds in our region of space, the only consciousness for dozens or hundreds of light years in any direction. This makes what we do matter more, not less. Every act of kindness, every discovery, every work of art, every moment of joy or connection or understanding, it all matters because it is happening here and now, and might not be happening anywhere else nearby. We are alone, but we are also important. We are small, but we are also precious. We are insignificant in cosmic terms, but we are also irreplaceable because there might not be anyone else like us for light years in any direction. Tonight, we have explored the light year in depth. We have examined what it signifies, how it is measured, what distances it represents, and its implications for understanding the universe. We have made a voyage from the familiar scales of our everyday existence to the almost incomprehensible scales of cosmic distance. A light year is 9.46 trillion kilometers. The distance light travels in 1 year, moving at 300,000 kilometers per second. It is the unit astronomers employ because kilometers and other terrestrial units of measurement become completely unwieldy when dealing with cosmic distances. When you are measuring distances to stars and galaxies, you require a unit that is large enough to make the numbers manageable while still being based on something physical and measurable. The nearest star to our sun, Proxima Centauri is 4.24 light-years distant. That is the closest stellar neighbor we possess, and it is still so distant that with current technology, it would require thousands of years to reach it. Our galaxy, the Milky Way, is approximately 100,000 light-years across from one edge to the other. To cross our own galaxy at the velocity of light, you would require 100,000 years. The observable universe is 93 billion light-years across, containing an estimated 2 trillion galaxies, each with billions or trillions of stars. When you observe stars in the night sky, you are not observing them as they exist right now. You are observing light that has traveled for years or centuries or even millennia to reach your eyes. You are literally gazing into the past. Sirius, the brightest star in the night sky, is 8.6 light-years distant. You are observing it as it existed 8.6 years ago. Betelgeuse, the red supergiant in Orion, is approximately 550 light-years distant. You are observing it as it existed during the Renaissance, over 5 centuries ago. A light year connects distance and duration in a fundamental way, demonstrating that they are unified aspects of spacetime rather than separate concepts. The velocity of light is a fundamental velocity limit built into the structure of the universe. Nothing can travel faster than light. This is not a technological limitation that we might overcome with superior engineering. It is a law of physics, a consequence of how space-time functions. This signifies that distances measured in light years represent real barriers to communication and travel. Stars that are light years distant are separated from us not merely by space, but by duration. Even traveling at the velocity of light, which is impossible for anything with mass, you would still require years to reach nearby stars, and thousands or millions of years to reach distant galaxies. The universe is expanding, and that expansion is accelerating. Dark energy, a mysterious force we do not comprehend, is pushing the universe apart at an ever-increasing rate. Distant galaxies are receding from us as space expands between us and them. In the far future, billions of years from now, the universe will be substantially emptier from our perspective, as more and more galaxies are pushed beyond our cosmic horizon, carried away by the expansion of space faster than their light can reach us. Despite these vast distances and fundamental barriers, despite the isolation imposed by the light year, we have learned an enormous amount about the universe. We have mapped billions of stars, measuring their distances with ever-increasing precision. We have detected thousands of exoplanets orbiting other stars, some of them potentially habitable. We have observed galaxies billions of light-years distant, observing them as they existed in the early universe shortly after the Big Bang. The light year has been our fundamental tool for measuring and understanding these cosmic distances, for mapping the universe and our place within it. Let us conclude where we commenced. A light year is the distance light travels in 1 year, 9.46 trillion kilometers. A number so enormous, it challenges our ability to comprehend it. A distance so immense, it makes our planet seem infinitesimally small by comparison. But you do not need to fully comprehend it intuitively to appreciate what it represents. You can appreciate that the universe is vast beyond our ability to fully grasp. You can appreciate that light from distant stars has been traveling for years, decades, centuries, or even millennia to reach your eyes tonight. You can appreciate that we inhabit a tiny corner of an enormous cosmos on a small planet, orbiting an ordinary star in one galaxy among trillions. There is something profoundly humbling about understanding light years and the distances they represent. It reminds us how small we are in the grand scheme of things, how brief our individual existences are compared to cosmic timescales, how isolated we are in space, separated from even our nearest stellar neighbors by distances that would require thousands of years to cross with any technology we can currently construct. It positions our concerns and worries and problems into perspective, demonstrating that from a cosmic viewpoint, the things that seem so important in our daily existence are temporary and local. But there is also something empowering about this knowledge. We figured this out. Despite being small creatures on a small planet, we measured these vast distances. We comprehended our place in the universe. We constructed telescopes and spacecraft and developed mathematical frameworks that permitted us to observe and comprehend things billions of light years distant. We are tiny, confined to one small world for now. but we are also remarkably capable. We are conscious beings who can comprehend the universe that created us, who can gaze up at the night sky and comprehend what we are observing, who can contemplate distances measured in trillions of kilometers and time spans measured in billions of years. From a cosmic perspective, you are insignificant. Your existence is a brief flicker, lasting perhaps 80 or 90 years if you are fortunate, in a universe that is 13.8 billion years old and will continue for trillions of years more. You exist for the blink of an eye on a tiny planet orbiting an ordinary star. But you are also remarkable in your own way. You are made of atoms forged in the hearts of stars that died billions of years ago. Their matter scattered across space and eventually recycled into new stars and planets, and ultimately into you. You are literally made of stardust, the product of cosmic processes that have been operating for billions of years. You are a way for the universe to know itself, to understand itself, to appreciate its own vastness and beauty and complexity. So the next time you gaze up at the stars on a clear night, remember what you have learned tonight. Those points of light scattered across the darkness are not merely lights. They are distant suns, massive spheres of fusing hydrogen, each one potentially hosting its own system of planets and moons. They are light years distant, separated from us by distances so immense that the light entering your eye right now, the photons that traveled across space to reach you, has been traveling for years or centuries. Some of that light commenced its voyage before you were born. Some of it departed its star before your grandparents were born. You are connected to those distant stars across the vast distances of space and duration, linked by light that has crossed the cosmic void to reach you. The universe is large beyond comprehension. You are small, a single person on a single planet. But you are here, and you can understand, at least conceptually, if not intuitively, what a light year genuinely signifies. You can grasp that the universe is measured in these vast units, that space is filled with distances that dwarf anything in human experience. And that understanding, that ability to comprehend your place in the cosmos, is extraordinary. It is what makes us human, what separates us from other life on Earth. We can gaze up and comprehend what we are observing. We can contemplate infinity and our own smallness simultaneously. We can feel both humbled and empowered by the same knowledge. And perhaps that is the most important thing to take away from understanding light years. Not merely the technical definition, not merely the mathematics of 9.46 trillion kilometers, but what it signifies for us as a species, for our future, for our place in the cosmos. We stand at a unique moment in history. We are the first generation of humans to genuinely comprehend the scale of the universe. Our ancestors gazed up at the same stars, wondered about the same questions, but they did not possess the tools or knowledge to measure the answers. They could not know that the stars were distant suns. They could not know that those suns were light years distant. They could not comprehend the vast distances that separate us from the rest of the universe. But we can. We have measured these distances. We have calculated them precisely. We know that Proxima Centauri is 4.24 light-years distant. We know that the Andromeda Galaxy is 2.5 million light-years distant. We know that the observable universe stretches 93 billion light-years across space. These are not guesses or estimates. They are measurements backed by decades of careful observation and calculation. This knowledge transforms us. It has to. When you genuinely comprehend that the nearest star would require thousands of years to reach with our current technology, when you grasp that the light from distant galaxies has been traveling for billions of years to reach your eyes, when you comprehend that we might be fundamentally isolated by the vast distances of space, it shifts your perspective on everything. It makes our differences seem smaller. The things we argue about, the borders we draw, the conflicts we engage in, all of it happens on one tiny planet in a vast cosmos. We are all together on this small world, separated from our nearest stellar neighbors by distances measured in light years. From that perspective, the things that divide us seem less important than the things we share. It also makes our existence seem more precious. If we are alone, or effectively alone because we cannot reach anyone else across the light years that separate us, then what we do here matters enormously. We might be the only consciousness in our region of space, the only minds that can contemplate the universe and comprehend what they are observing, the only beings who can create art, discover scientific truths, feel love and compassion and wonder. That is a profound responsibility. It signifies we need to care for this planet, this tiny island of life in the cosmic ocean. It signifies we need to preserve and protect the knowledge we have gained, the understanding we have developed. It signifies we need to think long term, not merely about the next year or decade, but about the next century, the next millennium, the long future of humanity among the stars. The light year is more than merely a unit of measurement. It is a reminder of our place in the universe, a reminder that we are part of something vastly larger than ourselves, but also that we are unique and precious within that vastness. A reminder that the stars are both incredibly distant and intimately connected to us through the light that bridges the cosmic distances. Every time you gaze up at the night sky, you are participating in something ancient and profound. You are observing across light years. You are gazing back in duration. You are witnessing the universe in all its glory. And you are part of that universe, made of the same atoms, following the same physical laws, connected by the same fundamental forces that govern everything from the smallest particle to the largest galaxy cluster. That is what a light year genuinely signifies. Not merely distance, but connection. Not merely isolation, but belonging. Not merely our smallness, but our significance within that smallness. Thank you for joining me on this voyage through space and duration. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the cosmos. And remember, even though light years represent distances almost beyond comprehension, they are also what connect us to the stars. Every time you gaze up at the night sky, you are observing across light years. You are observing the universe. And the universe, vast as it is yours to explore. Good night, and may you never gaze at the stars the same way again.